Hey guys, welcome back to my channel. I'm back with another video in the mathematical modeling video series. So in the previous video, we took a small break from modeling new things, and we started discussing about stability analysis. So today we'll be continuing with the concept of stability analysis. So in the previous video, we spoke about linear planar systems, systems of the form x dash equal to ax plus by and y dash equal to cx plus dy. We call these planar systems because they're in two dimensions, and they're linear because there's no non-linear term with x and y. Then we first discussed about the solution for a one-dimensional system x dash equal to ax. So that's just x of t is equal to e power at and some constant times that. And then we discussed about how the stability is discussed for this based on the value of a. And then we used that to talk about the stability in the case of a planar system where the planar matrix is a, b, c, d. And we said we find the eigenvalues lambda 1 comma lambda 2 of this matrix, which is nothing but what shows up in the solution of the system of equations as lambda 1 and lambda 2 in the exponent of the exponential function, in the argument of the exponential function. And then we discussed that there are multiple cases possible, right? We discussed that lambda 1 and lambda 2 could be both real values, or they could both be complex, or they could both be equal. So just to go over it again, we discussed that lambda 1 comma lambda 2 could both be positive, in which case the system is unstable. We discussed lambda 1 comma lambda 2 could both be negative, in which case it's stable. We said that even if one of them is positive, so if either lambda 1 or lambda 2 is positive, we can say it's unstable. Now if they're both equal, then again it depends. If it's positive, we know it's unstable, and we know if it's negative, it's stable. So now the only case which we didn't discuss in depth in the previous video was about complex eigenvalues. So now complex eigenvalues, there are multiple things possible, right? So either we could have that okay, so let's just erase some of this to make it easier. So we're talking about complex eigenvalues, right? And complex eigenvalues are of the form alpha plus or minus I beta. Now we discussed again, like in the previous video briefly, that if alpha is positive, we can say that it's unstable. If alpha is negative, it is stable. Now the question comes about if alpha is 0, but more in depth about the complex eigenvalues. So in real life, most equations that we model, if you solve for the eigenvalues, you are going to get complex eigenvalues. That's just how it is. Now the thing to understand is, whenever you have complex eigenvalues, the nature of the stability is usually it has some sort of periodic nature to it. And what I mean by that is that there are some particular curves that you have to understand when we talk about eigenvalues in the complex case. So when we talk about the complex case, because we have E alpha plus or minus I beta times t, we know that a sine or a cos term will come into the picture because of the imaginary part. Now, even if you guys aren't aware of complex numbers, it's fine. I'm not going to be going into the depth of it because that's not our main topic at hand here. But it's just important to understand that there will be oscillatory behavior in complex eigenvalues, and if you want to learn more about it, you can just look it up online, and you'll go into the depths of why it's actually oscillatory behavior and all of that. But what's important to understand is, think of it in the terms of a pendulum, right? When a pendulum swings, we have all learned in physics that there's a sine term involved. So we call it an oscillation. Now, usually what we do is we say that there's we ignore all the friction present in the air, like the air drag and all of that. So we say that yes, if you start oscillating, it'll keep oscillating forever. But that's not actually true, is it? If we were to include the air drag, right, what would happen is that it would eventually come to a stop. So it's somewhat the similar concept over here. So when alpha is less than 0, what we mean by stable is that it's a dampening oscillator, right? It's a damped oscillator, and the oscillations pretty much come to the origin or come to the equilibrium point. Therefore, it is stable. But if alpha is greater than 0, it's an undamped, an unstable oscillator. So which means it goes away from the equilibrium point in such a way that it can't return back to the equilibrium point. But now if alpha is equal to 0, that's somewhat like a stationary oscillator in the sense that it's an undamped oscillator. So there's no damping, so which means it doesn't come back to the origin. It's not unstable, which means it doesn't go away from the origin. Wherever it starts, it just oscillates around that equilibrium point. So we don't usually use unstable, we don't usually use stable for this case, right? It is not desirable. We don't desire this in general. So you could think of it as an unstable system, but I just wanted to explain this complex eigenvalues case a bit more as to what this alpha actually represents. Now we will come back to this once we start using these concepts in the models that we discussed, because like I said, most of the models that we've discussed and most of the models in real life scenarios end up having complex eigenvalues. Cool. So now that I've just gone through a brief overview and discussed the complex eigenvalues case, we can move to nonlinear systems. Now the SI model which we discussed, which was S dash equal to minus beta SI and I dash equal to plus beta SI. This is a nonlinear system because of the product of the S and I term. This makes this system, this S into I term makes the system nonlinear. So how do we discuss about the stability of nonlinear systems? We already know to find equilibrium points, you simply equate S dash equal to 0, I dash equal to 0, you solve them simultaneously and you get some equilibrium point. Then what do we do with that? So in the linear system, we simply had to directly take the A matrix and then find out the eigenvalues, and then that was pretty much it, right? And we were always discussing it about the origin. But now for nonlinear systems, we use a similar concept. We basically convert the nonlinear system to a linear system about the equilibrium point, and this process is called linearization. So for those of you who are math majors or have dealt with linearization, or even if you're from a physics background, you will know what linearization is. If you don't, it's essentially just converting a nonlinear system to a linear system about a particular point. Now to discuss stability, we are going to be doing it about the equilibrium points. And the way you linearize a nonlinear system is by actually taking the Jacobian. So what is the Jacobian? So let's say that we had sorry about that. Let's say we had dH by dt equal to f and dP by dt equal to g. And f comma g are both functions of h comma p. So this is f h comma p. This is also g h comma p, which means they're both functions of h comma p. And this is and f and g are nonlinear. So f and g are nonlinear. So how do we find the Jacobian. What is the Jacobian? So the Jacobian, it's usually denoted by J, okay? But to keep in line with our general notations, I'm going to call it A. So A, which is nothing but the Jacobian, will be the matrix dou F by dou H, dou F by dou P, dou G by dou H, dou G by dou P. Now this is the Jacobian matrix. So again, it's because we have two dimensions, it will be a two-dimensional matrix. But the thing is, you can't this is not the linearized matrix yet. So this is just a matrix, and we have to evaluate this, which means we have to evaluate this at H equal to H star and P equal to P star. So H star comma P star is an equilibrium point. So once I evaluate this matrix at the equilibrium point, so first I find the Jacobian, which is dou F by dou H, dou F by dou P, dou G by dou H, dou G by dou P. I found this matrix. Obviously there will be some, in each of those four terms, there will be P and H in it because it's a nonlinear system. Now I'll replace those H and P with the particular equilibrium point. So let's say the origin was an equilibrium point, then I will evaluate this matrix at 0, 0. Then I'll get the matrix A, which has only numbers in it, no variables, it has just numbers. Then I can find the eigenvalues of A, and it's literally similar to the linear case. So if I get positive eigenvalues, unstable, negative eigenvalues, stable, complex eigenvalues depends on the value of the real part. If both are equal, again, if it's a negative eigenvalue, stable. If it's positive, unstable, simple. So this is the procedure you use to convert a nonlinear system to a linear system. Now, a thing to notice is that so far we spoke only about 2 cross 2 matrices, right? This is for A. That's because we were only talking about two variables x comma y, because we thought of it as planar systems. But okay, now what if there are n variables? So what happens if there are n variables? Because we've already discussed the SIR model, right? So SIR, that's a three-dimensional model. So how do we discuss the stability there? So how do you extend the 2 by 2 case to the n by n case? That's what we have to deal with next. But we will not do that in today's video. We'll probably do that in the next video. In today's video, we'll just maybe take probably an example of sorts and we can try solving it. That would be the easiest thing to do. So now let's just take an example of x dash equal to y, y dash equal to 2x plus y. So first thing to do is we have to find the equilibrium points. So we equate x dash equal to 0. This implies y is equal to 0 and y dash equal to 0. This implies 2x plus y equal to 0. So therefore the only equilibrium point is 0, 0. Now the A matrix is 0, 1, 2, 1. Correct. Now the eigenvalues of these matrix, I hope everyone knows how to find the eigenvalues of this matrix. You essentially find the determinant of A minus lambda I equal to 0 and you get a quadratic equation. You solve that. So the quadratic equation you get is lambda square minus lambda minus 2 equal to 0. This implies that lambda is equal to, let's say lambda 1 is equal to 2, lambda 2 is equal to minus half. Now, because one is positive, one is negative, it's in fact an unstable equilibrium point. Moreover, if you have one positive and one negative in a 2D planar case, this is a 2D planar case, you can call this a saddle point. So which is an unstable equilibrium point. You can either call it saddle point, which is the right thing to do, or a saddle node is also correct, or you could just say it's an unstable equilibrium point because there's one positive and one negative eigenvalue. Okay, so now let's do another question, and this time we'll take a nonlinear system. So the system is x dash is equal to x square plus y and y dash is equal to y square minus 16. So to find the equilibrium points, we just equate both of them to 0 and solve simultaneously. So we have y square is equal to 16 and x square is equal to minus y. So this gives us y is equal to plus or minus 4. So let's say if it's plus 4, we have x square is equal to minus 4, which is not possible because a square can never be negative, correct? But on the other hand, if this is minus 4, then you have x square is equal to plus 4, which further gives us two things, which means x can be plus 2, x can be minus 2. So there are two equilibrium points in this case, and they are 2 comma minus 4 and minus 2 comma minus 4. So we'll call this point E1 and this point E2. So like I've already said, now we have to find the Jacobian. So how do we find the Jacobian? You do dou f by dou x, dou f by dou y, dou g by dou x, dou g by dou y, and evaluate it at E. So first we'll plug in E1, find the stability, then we'll plug in E2, find the stability. But first, what is the Jacobian matrix? We'll calculate that now. So when I do dou f by dou x, I get 2x. Dou f by dou y is 1. Dou g by dou x is 0 because there is no x term in g of x comma y. And then this is 2y, and I have to evaluate this at E. So first we'll evaluate it at E1. So let me just make the pen a little bigger. So A evaluated at E1 is nothing but 2x 1 0 2y at 2 comma minus 4. That's nothing but 4 1 0 minus 8. And to find the eigenvalues of this, we do determinant of a minus lambda I equal to 0. That will give us the determinant of 4 minus lambda 1 0 minus 8 minus lambda is equal to 0. And on solving this, what do we get? We get 8 plus lambda into 4 minus lambda equal to 0. Right? So we get two eigenvalues. One is minus 8 and the other is plus 4. So you can see one is positive, one is negative. Therefore, we can call this a saddle. Saddle node would be more accurate. So that means this nonlinear system behaves in an unstable manner. It is a saddle node at the equilibrium point E1. Correct? Like I said, we always discuss stability about equilibrium points. So now let's check about the second equilibrium point. So that means A evaluated at E2 is nothing but 2x 1 0 2y, and I evaluate this at minus 2 comma minus 4, I think, right? That's minus 2 comma minus 4. That is E2, correct? So that means what I get here is minus 4 1 0 minus 8. So again, determinant of a minus lambda I equal to 0 would give me 4 plus lambda plus 4 into lambda plus 8 is equal to 0. This implies lambda is equal to minus 4 and minus 8. Therefore, there are two eigenvalues, obviously, because it's a 2D system and both are negative. Therefore, E2 is a stable equilibrium point, or we could say the system is stable around the equilibrium point E2. So I hope that clears the whole thing about how to find stability for a linear system, how to find it for a non-linear system, how to find the Jacobian, how to evaluate the eigenvalues. Now the only thing left for us is to discuss how to extend this 1 by 1 and 2 by 2 matrix case, basically 1 variable and 2 variable case, to n variables, which we will deal with that in the next lecture. So thank you so much for watching. I hope everything is clear, and if you have any doubts, make sure you comment. Thank you so much for watching, and I'll see you next week.